Hello everyone, I hope you're doing well. I wanted to talk to you about the definition of the derivative. So before we were talking about rates of change, the average rate of change and the instantaneous rate of change. And this is basically calculating the slope of a secant line or a tangent line. So if we're looking at the average rate of change between 2 points, we have the secant line. And then if we move this second point B closer and closer to A, we're going to get the instantaneous rate of change at that point A. And I'm going to sketch out this idea from you because this is how we're going to end up getting the definition of a derivative from looking at the average rate of change, which is basically rise over run. Okay, so let's say that we have this point A here and this other point up here for our function, and then we connect them. Woo. Let's try that again. There we go. Okay, so say we have this line here. Now let's say that we move down to this point and we want to draw another secant line. We're going to get roughly this. Okay, we're just going to pretend that all of these are going through the same points down here. Okay. And now we're going to take a step closer to A and draw another secant line. And then we're going to take a step closer again. Ooh, that's not a secant line. And draw another one. And we're going to take another step. And then finally, when we're finally at A, we get our tangent line here. Okay, so this is our tangent line. This is our tangent. And then we had all of these secant lines in purple, and they kept getting closer and closer to the point of interest. So secant 1, secant 2, and then we went to 3, to 4, to 5, and then we finally got our tangent line. So this process right here, from sliding down this curve, f of x, sliding down f of x, this is the concept of a limit. Okay, as we get closer and closer to that point. And this is how we define the limit. Specifically, the tangent line. So the slope of that tangent line, that red line that I drew there, so the tangent line, that slope is defined basically as the instantaneous rate of change. So the tangent line of a graph, f of x or y, okay, graph function, they're used interchangeably. At this point A and f of a, and remember sometimes we rename this and call this b, is a line through the point having a slope, the limit, as h goes to 0, of f, we were looking at the point A in particular, so f at a plus h, minus f at a, all divided by h. Provided the limit exists, of course. And if the limit does not exist, then we say that there is no tangent at that point. Okay. Now, the slope of a tangent line at a point is also called the slope of the curve. My cat is jumping all over the place. Is the slope of the curve at that point and corresponds to the instantaneous rate of change of y with respect to x at that point. So basically what this does is it indicates the direction of the curve at that point. Of the curve at that point. Okay. Now, let's do an exercise where we're looking at, say, the plot of a standard parabola that's shifted up by 2. And we're going to find the equation of the secant line through the points -1 and 2. So this is like our A, and this is like our B in our equation. And so we know how to find the actual slope of the secant line. That's that f at B minus f at A. So f of 2 minus f at -1. And then we divide that by B minus A, or in our case, 2 minus -1. And now what we're going to do is we're going to sub these values into our function here. Okay, so we're going to have our f of 2 expression minus our f at -1 expression, and then 2 minus -1, that's just going to be 3. Okay, so we're going to have our x parts squared plus 2, and then our x parts squared plus 2. Okay, and here our x is 2, and here it's -1. All right, so we're going to end up getting 6 minus 3 over 3. So that's 3 over 3, so that's 1. So if we think about the equation y is equal to mx plus b, this here is just our slope m. So now we want to find the secant's equation, y is equal to mx plus b, where I've already found my slope. And I also am given 2 points. This is another way we could have set it up, but I wanted to just do it through the definition with you. But we know what the 2 points are, so we could have done the y2 minus y1 over x2 minus x1. So the first point that we had was -1. The y value, to find it, we would have to plug the -1 into the function, which we secretly already did with how we calculated the slope before. And the second point, we were given the 2. To find the corresponding y value, we would have to plug 2 into f, which we already secretly did the last page. And this would give us 2 and 6. And now, just like you would for the equation of a line, you can pick any point. So let's just say we pick the point -1, 3. We still have to find this b, this y-intercept. So I'm going to pick this point, and I'm going to plug in my values that I have now, and then I'm going to isolate for my b. Okay, so this is 3, this is 1, this is -1. So I have 3 minus 1 plus b. So my b is equal to 4. And so the slope of the secant line would just be y is equal to x plus 4. Now, using the same function, let's find the equation of the tangent line through the point x is equal to -1. So x is equal to -1, this is like our a. So if we wanted to find the slope of that tangent line, that's the definition we just looked at. The limit as h approaches 0 of f at a plus h, okay, at a particular point a, minus f at a, all divided by h. Okay, and what we're going to do is we're just going to rewrite this expression, but I'm going to sub in what my a is. So in this case, my a is equal to, get rid of this, get rid of this. The a that we're interested in is -1. Okay. So now, and just a quick little thing about writing this, what I'm going to do for convenience, when I'm going to sub in these expressions here, okay, this just looks a little bit cluttered. So what I'm going to personally do is I'm going to write this as the limit as h goes to 0, and I'm going to go 1 over h, and then I'm going to sub everything in here. Okay, you don't have to do this. It's totally up to you. But I find it a little bit easier if you get overwhelmed with the algebra. So I have 1 over h, now I can do big brackets. So I need to look at -1 plus h into the x value, and my function is x squared plus 2. Okay, so this is the f at a plus h, or -1 plus h, and then we have minus, and then I need to look at f of -1. So I got my -1 squared plus 2. And then we have the limit as h goes to 0 of 1 over h. And now I'm going to have to expand this, okay, using FOIL. So -1 times -1 is 1. Minus h minus another h, so minus 2h, and I'll do this here. Plus h squared plus 2 minus, this one I'm going to keep brackets here for a second to make sure I just don't make a mistake. So 1 plus 2, so this is 3. And now we can simplify things a little bit. Okay, this is going to become a 1. 1 plus 2 is 3, but we're taking a 3 off, so that simplifies. The limit as h goes to 0, 1 over h. Now what am I left with here? I'm only left with things with h's, so minus 2h plus h squared. Now keep in mind, this is all divided by h, so I can cancel out one of the factors of h from each term. So I have the limit as h goes to 0, no more 1 over h, that's gone now. What do I have left over? I have minus 2 plus h. I can't simplify this anymore, so now I can plug this into here, and I'm left with my slope of my tangent line, minus 2. But we're not done yet. So the slope of the tangent line, what point are we interested? We're interested at the point -1, and to find the y value, we would plug -1 into our function. So that gives us our -1, 3, which we knew from before. And tangent line at this is -2. And what do we need? We need y is equal to mx plus b for this tangent line. And then we're going to plug everything in. We're going to plug in our y, we're going to plug in our m, our x, and then we're going to isolate for our b. Okay, so what's my y in this case? I have 3, -2, I have -1. So I have 3, 2 plus b. So 1 is equal to my b, and therefore the equation of my tangent line, -2x plus 1, at the point -1. All right. Okay, so there's how we can find the equation of a secant line or a tangent line. Now, in terms of notation, provided that the limit of a function y is equal to f of x exists at a point x is equal to a in its domain, we use the notation. So in English, we say f prime of a. So let me write this in here. So f prime, like Optimus Prime, f prime of a, to denote this limit. So this slope of the tangent line, we call this f prime of a. Okay, so for each number a, we can obtain a number f prime of a by calculating this limit. Oops, sorry, my head's in the way. And this defines for us a new function. This defines for us the derivative. So the derivative of a function, real valued function, at x, so now I'm doing it for all the values of x in the domain, not just a particular point a. So the derivative of this function is, in terms of notation, I call it f prime of x, and then this is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And then if you want this at a specific value for x, so called a, so say in the last example -1, then we can sub -1 in at the end. And this is provided the limit exists. And this is referred to, f prime of x is called the derivative of f. And we're saying what we differentiate with respect to. So with respect to x. Now there are some other notations. So another notation, for example, is df dx. Some people also use dot notation. So usually these are physicists. Something like this. Okay, so normally we'll be using this notation or this notation. Okay, but for now it's advantageous for us just to use the f prime notation. There's a whole bunch of other notations as well. but we'll stick with this one for now and introduce new ones as we use them. Okay, so if if x is a value in the domain of f and f prime exists, then f has a special name. It's called differentiable at x. So we had if a function was continuous, now we also have a function if it's differentiable or not. And there's a special relationship between a differentiable function compared to a continuous function, and we'll talk about that in the next video. Okay, so this is differentiable at x, and the actual process of finding the derivative, this f prime, that is called differentiation. Okay, so the actual function is called the derivative. The process of finding the derivative is called differentiation. And if you can find the derivative, if you can differentiate, then the function is called differentiable. Okay? Nice little tongue twister for you there. Okay. Now let's do an example where we find the derivative. So not now just at a particular point, but in general. So for all the x in the domain. So let's find the derivative of f of x is equal to x squared, and then afterwards, we'll see what it is at 2. So by definition means you have to do it using the definition. The definition is with the limit. So the limit as h goes to 0 of f at x plus h minus f at x all over h. And another way that you could approach it, so if you still found plugging everything into the limit like this overwhelming, break it down step by step. Let's look to see what this is, look to see what this is, subtract them, and then find all the parts and then plug them into the limit at the end. So if you find you get overwhelmed with the algebra, that's what I would recommend doing. So what is our f of x? Well, that's just x squared. What is our f at x plus h? So the thing that I'm plugging in here is my x plus h, and then I have to square that. Okay, so by FOIL, we have x squared plus xh plus hx. Okay, so plus 2xh plus h squared. So then if you want to subtract them, this x squared plus 2xh plus h squared minus x squared, I'm going to be left with 2xh plus h squared. So now that I've simplified some of the algebra, now what I'm going to do is I'm going to plug it into the definition of my derivative. So I have the limit as h goes to 0 of that f of x plus h minus f at x all over h. And when you're actually doing this part, you're going to have to always write the limit. Okay, so my numerator I found was 2xh plus h squared. And then all of this was divided by my h. Now I have an h in each term at the top, so I'm going to be able to get rid of one of the h's for each term on the top and then the one on the bottom. And I'm going to be left with 2x plus h. I cannot simplify this anymore, so now I can sub in my 0 into my h, and what am I left with? 2x. And if I look at the specific point of 2, okay, so I plug 2 into here, I get a value of 4. Okay, and this is, so which is the slope of the function that we looked at, so the f of x is equal to x squared, at the point 2 f of 2. Okay, so that's what this physically represents. All right, now let's do one that algebraically is a little bit more complicated. Okay, but the process is exactly the same. Using the definition of a derivative, we want to find the derivative of 4 divided by x. So I know what this definition is. It's the limit as h goes to 0. You're going to write this out so many times by the end of this video, you won't forget about it. F of x plus h minus f at x all over h. And let's break this up step by step. So what's our f of x? Well, this is 4 over x. What is our f at x plus h? Well, now instead of x at the bottom, I have an x plus h. And now what I want to do is I want to subtract them. Okay, so I want to go 4 divided by x plus h minus 4 divided by x. Okay, so I need to combine these somehow. But in order to do that, I have to have a common denominator. Okay, so I'm going to multiply the first term, the top and bottom, by x. And my second term, I'm going to need the x plus h. So I'm going to multiply the top and bottom by x plus h. Okay, and this is an example where it's good to split it up just because the algebra is a little bit trickier. But now our denominator is the same. So I have on my top 4x minus 4 times x plus h, all divided by x plus h on the bottom. Now, if you wanted to, you could expand the bottom, but for now I would say just leave it because, you know, maybe we're going to be able to more easily cancel things out. It may be a little bit easier to see what happens. Now let's expand at least the top because there we're going to be able to simplify it. So we have 4x minus 4h, so we distribute that 4. And then on the bottom, I'm going to leave this as x plus h. But on the top, these cancel. And I'm just going to be left with my minus 4h all over x plus h. Okay. So now let's plug it in. Okay, so we have the limit as h goes to 0. When you're doing your questions for your assignments, for example, you only have to write out this definition once. I'm literally writing out this many times so you kind of get used to it. Okay, so you just get practice to help you memorize it. All right, so let's write down what we have. So on our numerator, we have this lovely expression, minus 4h times x plus h. And then all of this is divided by h. Okay, so this is an example where I really like writing the 1 over h out front. So what I mean is like this. So the limit as h goes to 0 of 1 over h like this. And then putting down whatever your numerator is. Okay, and we're allowed to do this because of the rules that we talked about earlier in the course. But then it's much easier to see what to do next. So I do have an h on the top and bottom that I can cancel. And then I'm going to be left with the limit. As h goes to 0, I no longer have that 1 over h. I only have negative 4 divided by x plus h. And now I can't simplify this anymore, so I can sub this h going to 0 into here. And I'm left with minus 4 over x squared as my derivative. Okay? So I hope you found this helpful. Thank you very much.